Okay, so one of the things we discussed about in the last lecture was intensity with respect to the amplitude and all that. So we saw that one-dimensional longitudinal harmonic waves, or basically 1D sound waves, they can be represented by two ways. They can be represented in terms of the displacement so-called displacement wave, where the displacement is longitudinal in nature. So that can be described in terms of a longitudinal displacement with a longitudinal amplitude of S0 sine omega t plus or minus kx, depending on the direction of propagation, plus some phase constant, okay, where all these things are standard. V is equal to f lambda, and we saw V is square root gamma RT by M, or square root of Bulk's modulus by density, or square root of Young's modulus by density, depending on the type of medium, gaseous medium, liquid medium, or solid medium. Okay. So again, frequency is the property of the source, right? Wave velocity or propagation speed is the property of the medium, and therefore lambda depends on both, because V is equal to f lambda. Then we saw that this kind of displacement wave also creates pressure variation. So particularly if you're looking at a sound wave or a longitudinal wave propagating through a fluid medium, a gaseous or a liquid medium, then the variation in pressure becomes the more important thing, okay, because that is what gives the physiological experience of sound. It's the way the pressure variation affects our nervous system, because it creates vibrations of the eardrum, and that is picked up as the nervous system as sound signals, or is picked up as by the nervous system as electrical impulses, and then of course the brain interprets it as sound. So the variation in pressure becomes the more important thing for us here. So we saw also that if you compare the displacement wave with the pressure wave, the pressure amplitude is directly proportional to the displacement amplitude, and the phase constant for the pressure wave always has a pi by 2 relation with the phase constant for the displacement wave. So basically there is that kind of relationship that when the particles are at their mean position of oscillation, the pressure is either at a compression maximum or rarefaction maximum, whereas the particles of the medium which are located at the extreme position of their oscillations, that is where the pressure variation is zero, or the volume stress or the bulk stress is zero. So this is okay. Fine. So then next thing we had seen was intensity of the sound wave. So intensity defined as energy propagated per unit area per unit time. So that intensity was half into rho v into omega square into S0 square, or what we can also write as half of square root of Bulk's modulus into density into omega square into S0 square. Of course, Bulk's modulus becomes an instantaneous quantity for a gaseous medium, so it becomes gamma into P, that we discussed in thermodynamics before. So that is. We also saw that this can be converted into intensity in the form of this thing, pressure amplitude. So it becomes like this. Yes, I am sending the notes, Shikhar, just now, even as we speak.
Sir?
Yes.
So the circular sound waves, like they come from point source, right? So for them, it's all same, the intensity and stuff.
Actually, yeah, rather than circular, no, it's spherical. So I'll explain that also, the geometry of those. So basically, they are radial waves where along each axis, which is radial axis emanating from that point source, you have that one-dimensional kind of wave. But instead of one single one-dimensional wave propagating through a windpipe, you have simultaneously infinite number of those, one-dimensional waves which are propagating in all the radial directions. Now you understood the point. Okay, so all of them are in phase.
So same for cylindrical also. source.
in the sense that if you have a medium which is like a rod shaped medium, like for example, if you have a metallic rod which is made to vibrate longitudinally, but then the waveform is actually a little bit more complex, because if you want to create cylindrically symmetric wavefronts, then actually you will have to have a cylindrical kind of rod, and the surface of the rod should vibrate radially. So that's something a little difficult to create.
Yes.
Understanding the point? It's like, you have a cylindrically shaped speaker. The diaphragm of the speaker should be like the surface of the cylinder, and it should vibrate accordingly.
Okay.
So
Yeah,
we don't really get into those complex kind of geometries over here, because it becomes quite out of hand mathematically. So
we don't have that.
mathematically,
We don't have that, right?
like that is quite advanced in physics. Like if you study a branch of physics called acoustics and sound engineering, then also, like, I mean, that's the theoretical part of it. Practically, you'll always be applying the concept of sound, like modeling it as one-dimensional waves which are traveling from the point source. Because compared to your system, you'll always treat your source like a point source. Okay,
Yes.
and if your system has a large surface, the system which is emitting sound has a comparatively large surface, then rather than think of it as an entire surface which is vibrating, you can think of it like a collection of point sources.
Oh, understood, sir. Understood.
So
Yeah.
ultimately, the waves that are generated from them in the space around them, they are basically as a result of superposition of waves from all the collection of point sources.
Okay.
Yeah, so that itself becomes quite complicated, and like if you really want to get into it, then one has to do like simulation and computer modeling of it. Okay,
Okay.
but
Okay.
there are of course ways to really simplify the matter and understand it subjectively, and that is how the subject of acoustics actually deals with it. So in acoustics, you will hear things like diffusion of sound, echo, flutter echo, comb echo,
Yes.
comb filtering because of frequencies, because of echo effect and all that. So these are some kind of qualitative analysis of this kind of phenomena which are happening, which is required for that particular subject and its application. Okay,
Yes.
anyhow, so
Understood.
that's a different, I mean, that's a more advanced part of the application altogether. So without getting into all that, so here what happens is, yeah, so I'm coming back to that point source thing. Okay, but first let's quickly just understand this concept of intensity. So intensity is expressed in, so intensity, when we express it like this, or when we express it like this, so basically intensity is proportional to square of amplitude, whether we think of it as the pressure amplitude or the displacement amplitude, and this intensity is expressed in watts per meter square. When we actually do a calculation of the intensity, it will be expressed like this in watts per meter square. But because the range of intensity for the human hearing we discussed about is very large, the threshold of hearing we saw was something which was a comparatively very tiny intensity. The threshold of hearing was 1 picowatt, okay, picowatt per meter square, or basically 1 into 10 raised power minus 12 watt per meter square. Whereas the threshold of pain, which we can think of like maximum intensity on that scale, is 1 watt per meter square. So you can see it's a huge range. It's a range of 10 raised power 12 times. So to make
Yes.
that easier to handle with handle mathematically, and also because our hearing system is more attuned to a logarithmic kind of definition of intensity. So when you have some quantity expressed as a logarithmic quantity, then every time, for example, you double the quantity on the logarithmic scale, it increases by a factor of 0.3. Every time you multiply it by a factor of 10 on the logarithmic scale, it increases by a factor of 1. So our hearing system is actually like that, when you go from 1 to 10 to 100 to 1000, instead of perceiving the sound's loudness as increasing by 10 times, then by 100 times, then by 1000 times, we perceive that it's increasing by the same amount. So hence, basically, there is that logarithmic scale or the decibel scale, which actually expresses it as 10 times a logarithmic scale. So 10 times a logarithmic scale means that every time we double the intensity in watt per meter square, on the decibel scale, it increases by a factor of 3 dB. So decibel scale is the next thing we are
So it is
discussing.
it is a logarithmic equation to find decibel.
Yes. It is a way of expressing the intensity as a logarithmic relationship with respect to a reference intensity. And that reference intensity is chosen as what the threshold of hearing. So I naught is this one only, 1 into 10 raised power minus 12 watts per meter square. and that is only the threshold of hearing. So you can see that if you replace I with I naught in decibel scale, I naught in decibel scale will become 0 decibels because log 1 is 0. But for example, if you take an intensity of 2 times I naught, in the decibel scale, this intensity, let's say I1 is equal to 2 times, it will become 3 decibels because you doubled it. Then for example, if you take an intensity of, let's say 2 into 10 raised by 6 times the threshold of hearing. So in decibel scale, this will become 63 decibels because this thing 10 log 2 into 10 raised power 6 times I naught. That will give you 10 log 2 plus log 10 raised power 6. So that will give you 10 times 0.3 plus 6. So that's how it becomes 63 decibel. But now, for example, if you double this intensity, so it becomes, let's say 4 into 10 raised power 6 times the threshold of hearing, or that would make it 4 into 10 raised power minus 6 watts per meter square. Whereas this one would have been 2 into 10 raised power minus 6 watts per meter square. So this one in decibel scale now, I3, let's say this one is. So suppose I take I3 as double of I2. So you can see in decibel scale, I3 will become 63 decibel. 66 decibels. Then suppose you double this one now. So I4 is, let's say 2 times I3. So it becomes 8 into 10 raised power 6 times the threshold of hearing, or it becomes 8 into 10 raised power minus 6 watts per meter square. So in decibels, I4 now becomes 69 decibels. So one thing you can notice that when you are increasing the intensity from I2 to I3, the increase in intensity in the this thing, in the decimal scale or in the watts per meter square scale is a factor of 3 into 10 raised power minus 6 watts per meter square. Because you've gone from 2 to, sorry, it is 2 into, gone from 2 into 4 into 10 raised power minus 6. And then when you're going from I3 to I4, the increase in watts per meter square is how much? The increase is 4 into 10 raised power minus 6 watts per meter square. You've gone from 4 to 8. But on the decibel scale, when you go from here to here, it is plus 3 dB. And then when you go from here to here also, it is plus 3 dB. So now as it turns out, when we do a listening test, a hearing test for these kind of changes in intensity, we will not feel like going from I3 to I4 is double the change as going from I2 to I3. We will actually feel like it's the same amount of change. So that is what we mean by saying that our perception of intensity of sound is logarithmic instead of being decibel. Okay. So this is, if you're just wondering why we use the decibel scale, it's not really something that's significant from your syllabus point of view. Just doing the calculation is important from the syllabus point of view. But why we have it in decibel scale is because our perception of sound seems to follow a logarithmic scale. So that's the thing. Okay. Now this plus 3 dB rule becomes something important, that every time we increase, we double the intensity in watts per meter square. On the decibel scale, there's a plus 3 dB increase. Or if we reduce the intensity by a factor of half in watts per meter square, then on the decibel scale, it will reduce by minus 3 dB. So that is now the concept that was related to the point source we were discussing about earlier. So if we have a point source of sound, now the point source is obviously not going to be exactly a point. You can just imagine like a speaker, which is like omnidirectional. So it sends sounds in all directions equally. So it's a very idealized situation that doesn't happen with a real life speaker, or it doesn't happen with any real life source of sound. Like even a tuning fork, it will actually not generate sound equally in all directions, because obviously the tuning fork is lying on some surface or there's some floor close to it. So there's reflection of sound happening from the floor. So it's not going to project sound equally in all directions in three-dimensional space. Now, that would be a situation where you take a very tiny source of sound and place it somewhere at a height in atmospheric air, and there should be no reflecting surfaces and nothing to dissipate sound, nothing to create friction and things like that anywhere close to it. So in that kind of idealized situation, if you have a point source of sound which is generating a power of P, so it is generating energy per unit time of P. So what happens is, from this point source in all directions, there are radially symmetric sound waves. You can understand the pressure variations like this, which are radially symmetric, equally in all directions. Okay. So as a
Sir, sir,
Just was confused.
yeah.
yeah, people, sorry. Yeah, so from a point source, yeah, somebody was asking some question. I think I
Sir,
cut for a moment. I think
hello,
I'm not able to hear. Just a second. Try again.
hello.
Yeah. Now it's clear, Piyush. Yes.
Sir, I wanted to ask you, it is said that tuning fork produces the purest note, right? Purest sound. So, is there any reason as to why it does, like, why
Yes,
did
I,
it
I
like?
will explain that point also to when we come to the concept of standing waves in sound. So actually, see what happens is that any source of sound which is creating what is called a sound of a pure pitch is actually generating sound of a certain frequency and its harmonics. It is very, very rare that you have a source which creates a pure tone which is only at one particular frequency. Okay,
Okay.
there need to be some idealized conditions for that to happen. Okay, so tuning fork is a device which, like, almost perfectly follows that ideal condition, that is generating sound of a pure tone or a particular frequency. But yeah, I mean, electronically you can create sound which is purer than that of the tuning fork, because you can send an electrical signal into a speaker's diaphragm, I mean into a speaker's coil, which is of a single frequency tone, because it's being controlled by electrical circuit. Then the diaphragm of the speaker will vibrate in such a way that it creates almost a pure tone. But yeah, out of natural acoustic sources, the only way you can do that is something like a tuning fork. Because if you pluck a string or use some kind of wind instrument to create harmonic waves, what will happen is, always along with the fundamental frequency, there will be the overtones also which are present. That is the harmonic frequencies. So you will not get a pure tone. You will get a
Yes.
pure pitch, but not a pure tone.
Okay.
So
Understood, sir.
okay, so I think you'll be able to understand this explanation better once we come to standing waves. Okay, so just hang on a little bit, like in bit of time we will come to standing waves. Okay.
Yes, sir.
Okay, so what is happening is, for a point source, okay, if it is generating power P, so that is in joules per second, okay, or watts, okay, then this power is distributed uniformly in three-dimensional space around it through the propagation of spherically symmetric radial waves. Okay, so that is the idealized version of it. Okay. So through the propagation of spherically symmetric radial waves. So hence, if you now consider all points on a surface, on an imaginary spherical surface, with that one as the center, just like you consider a spherical Gaussian surface for a point charge, like that, if you have an imaginary spherical surface that you consider, then all points on that spherical surface are receiving equal distribution of energy. Okay, so Jagannath, if you're present, are you understanding this point? Like, I
Yes,
think
sir.
this was the question you had asked me last time after the lecture.
No, it was about some example you had. solve.
So that example was related to this only, that how from as the distance is increasing from the point source.
Yes, yes.
So that is related to this only now. Okay. So far this is clear, no?
Yes, sir.
So if you consider now an imaginary surface which is spherical, like a Gaussian surface you do in electrostatics, like that, consider an imaginary spherical surface at a distance r. So on a surface or at a distance r from the point source, the intensity, that is, at all points, will be the common value of P divided by 4 pi r square. Because that power generated by the source is getting equally distributed over all points on that surface, because the waves are radially symmetric. Okay, just like flux distribution becomes symmetric. No? So on the Gaussian surface like a sphere, the flux per unit area becomes phi divided by 4 pi r square, and the total flux is q upon epsilon naught. So that is how the flux distribution is basically the field, which is q upon 4 pi epsilon naught r square. So something very similar in visualization here also. Okay. So now you can see from this we understand that the intensity is inversely proportional to r square. But remember, this is the intensity not expressed in decibel. This is the intensity expressed in watts per meter square. Because you are dividing the power in watts divided by 4 pi r square surface area in meter square. So now because of this, what we can say is that if I double the distance, the intensity will become 1/4. If I half the distance, the intensity will become 4 times. Right? So that's how this comes. So for example, if I is equal to I1 at R equal to R1 in watts per meter square, then I equal to I2 at R equal to R2 will be, I2 will be equal to I1 by 4 if R2 is equal to 2R1, or I2 will be 4 I1 if R2 is equal to R1 by 2. If I come closer to the source by a factor of half the distance, then my intensity in watts per meter square will increase by a factor of 4-fold. Whereas if I move further away such that I'm doubling my distance, so every time I double my distance, my intensity will become 1/4. Okay. So on decibel scale, now what we can say is that, so therefore, if the intensity is x decibels at R equal to R1, then at 2 times R1, the intensity in decibels will become x plus 6 decibels, because it's become 4 times. So plus 3 plus 3. Whereas let's say R equal to R3, which is half of this. Sorry, this will be minus because it's becoming less. I'm doubling the distance, so it should be. So I2 in watts per meter square is I1 in watts per meter square divided by 4. Therefore, I2 in decibels will become I1 in decibels minus 6 decibels. Likewise, if I half the distance, then it will become x plus 6 in decibels. So, I mean, a simple thing is like this, that suppose we say that from a point source, the intensity at a distance of 20 meters is, let's say, 80 decibels. So find the intensity in decibels at a distance of, let's say, 40 meters, and then at distance of, let's say, 5 meters. So this is the information given to me that when I'm at a, so I mean, this point source could actually be something larger than a point source, because you're talking about a distance of 20 meters. So something which is, just a few inches or centimeters in size can be treated like a point source. So it might be a small speaker or something like that. So at a distance of 20 meters, if you're measuring the intensity of sound to be 80 decibels, then what is the likely intensity of sound you will be able to measure when you increase your distance from 20 to 40, or when you reduce your distance from 20 meters to 5 meters. Okay, so this is the type of calculation you should be able to do, understanding the decibel scale and the concept of variation of intensity with distance. Okay? Both of the concepts that we have written above, that variation of intensity with distance is like this, that intensity is inversely proportional to r square. Okay, and the decibel scale concept that you know is that every time you double the intensity, there is plus 3 dB rise, or every time you half the intensity, there is 3 dB loss. So using that concept. Okay, so let us discuss the answer to this. Try this out, people. Samarth, I've received your answer, but just check your calculation once more. Remember, the intensity I've given is in decibels, not in watts per meter square. Okay, so I'm just giving you the answers. Try to figure this out. So from 20 meters, when I increase the distance to 40 meters, I'm doubling the distance. So it should become from 80 to 74 decibels. So very good, Jagannath, you got this correct. Samarth, you got this correct. Okay, whereas when I'm reducing the distance to 5 meters, I'm reducing the distance by a factor of 1/4. Okay, so the intensity will increase by a factor of 16. So that is 2 to the power 4. So it's 3333. There will be a 12 decibel rise. Okay, so 92 decibels should be the sound. So I will demonstrate in a moment how I've done the calculation mentally like this. Okay.
Sir, it will be 104. Okay.
It will be 92 bit. I'll just show you the calculation.
Because it is 2 to the power 4 times. So 2 multiplied by 4, so each 3. Okay. Yes, it is.
Yeah, people, I will show you the calculation. Just a moment. Huh? Okay, now let's see how we can use that 3 dB rule to do this type of calculation very fast. If we were going by the concepts now, what we would have said here is that, okay, let the power of the source is suppose P. Okay, so then intensity at any distance R is P divided by 4 pi R square. So what is happening is P divided by 4 pi into 20 whole square is equal to our how much? It is our now that intensity we have to convert. That intensity at R equal to 20 meters was given to us as how much? 80 decibels. So we'll have to convert this. Okay. So that means that intensity in watts per meter square is how much? So 10 log I divided by I naught is equal to 80. So log I by I naught is 10, rather 8. So I by I naught is 10 raised power 8. So I is equal to 10 raised power minus 4 watts per meter square. So this is what we would have come to know, because I naught is 10 raised power minus 12. So then we would have put this here and we said okay, so this is 10 raised power minus 4 watts per meter square. So we have this, or we can calculate the power from this. So therefore now at R equal to 40 meters, the intensity will become how much? P divided by 4 pi into 40 square. So obviously you can see that that will become 10 raised power minus 4 divided by 4. So that is 0.25 into 10 raised power minus 4 in watts per meter square. And similarly, we would have also seen that suppose we are taking power at R equal to 5 meters. That would be P divided by 4 pi into 5 square. So 5 is 1/4 of 20. So this would have become 16 into 10 raised power minus 4 in watts per meter square. So now we'll convert this in decibels again. You'll see we'll get 10 log 16 into 10 raised power minus 4 divided by 10 raised power minus 12. That is 10 log 16 plus 10 raised power 8. So that kind of calculation we'd have to do. But this trick gives us something nice, okay, that we can. So the 16 is 2 to the power 3. Sorry, 2 to the power 4. So 4 log 2 plus 8 log 10. So that is 10 into 4 into 0.3 plus 8. So you can see that is how it is becoming 92 decibels. And similarly, this one, when we convert decibels, so it is 10 log 1 by 4 into 10 raised power minus 4, or 0.25 into 10 raised power minus 4 divided by 12. So it is 10 log 1 by 4 into 10 raised power 8. So it is 10 log 10 raised power 8 minus log 4. Okay, so 8 log 10 minus 2 log 2. That is how you get 74 decibels. Okay. But this whole calculation can be just simplified by using the simple trick that if I2 is twice I1 in watts per meter square, then I2 in decibels is equal to I1 in decibels plus 3. And similarly for half. Okay, so you can see here that at R equal to 20 meters, the intensity is equal to whatever 80 decibels. So at R2 equal to 40 meters, the intensity I2 will become I1 plus 3 plus 3. Sorry, minus 3 minus 3 in decibels, because I2 in watts per meter square is I1 in watt per meter square divided by 4. That also into a factor of. And similarly, the logic for when it is 16 times, because the distance is made 1/4. Okay, so this is just a quick calculation trick you should understand and remember. Yeah, Shikhar, and minimize it further. So this was the direct solution that I've done first. Okay. Explaining the logic, of course. Okay. This is a concept, now applying it to the question. Okay, so Shikhar, hope you have understood this calculation fully. Okay. So we are talking about audible sound for human beings, and we saw about the frequency range and the intensity range, and then decibel scale, and this particular thing of how intensity varies with distance from a point source. Okay, so this is an important concept to remember, that intensity is inversely proportional to square of distance. For example, later when we come to wave optics also, you will see that this will be taken into consideration in certain types of questions. Okay, now moving on to the next part about sound, which is very simple because it's similar to what we've done in transverse waves. Superposition of sound waves. Okay. So here, in addition to interference and standing waves, which are same type of thing, we will also study something called beats, which is different. Okay, but let's start in order. Okay. So the concept for interference is same, but the exact application is slightly different because you're talking about pressure waves and not waves along a string. Okay. So the first category of superposition for us called interference. Here the definition of interference actually becomes simpler than what it was for transverse waves. It becomes that two or more sound waves of identical frequency will superimpose to create interference. That's it. It need not be traveling in the same direction. So it could be a situation like this, that we have a point source of sound S1, which is at frequency F, and another point source of sound S2, which is at the same frequency F. So they are creating waves, and there is a detector or a listener somewhere here. Then a particular sound wave, a particular one-dimensional sound wave, will be reaching him from S1 and S2 respectively. You can visualize the variation in pressure reaching him like this. So if this has traveled a distance x1 and this has traveled a distance x2, then the wave from source S1, suppose that we denote by a pressure variation P1, is equal to some amplitude, let's say PA, into sine omega t minus kx1. And from source S2, it is having some different amplitude, let's say PB, but having the same omega, because it has the same frequency traveling through a different distance. It might have some initial phase difference like this, why not? So omega is equal to 2 pi f, where f is the common frequency of the two waves or the two sources, and k is equal to omega by v, or 2 pi by lambda, where v is speed of sound. So with the appropriate formula, depending on what kind of medium there is over here. So typically we are always talking about sound waves propagating through air. So we use the formula square root of gamma RT by m, where m is that, that weighted mean sort of molecular weight of air, taking into consideration that about 72% is nitrogen, and trace amounts of noble gases and comparatively large amount of oxygen also, and all that. So that kind of thing. And similarly for gamma. So now the net pressure variation due to the superposition, and this kind of superposition only is called interference of waves from the source S1 and S2. That net pressure variation becomes P1 plus P2. So it becomes PA sine omega t minus kx1 plus PB sine omega t minus kx2 plus phi naught. So we can write this as, you can say that this term omega t minus kx2 plus phi naught can be written as omega t minus kx1 plus some delta phi, where you can see delta phi is basically equal to how much? It is kx1 minus x2 plus phi naught. Okay. So this is the phase difference. For example, if the two sources were in phase, then phi naught would be 0, and the phase difference would be as a result of only the path difference x1 minus x2. So the quantity x1 minus x2 is the what we call the path difference. So the phase difference can be as a result of path difference. It can be as a result of some phase difference between the sources S1 and S2, and it can be as a result of the combination of these two things. Now, rest of the thing is same as what we have seen earlier. So we can just write this as PA sine omega t minus kx1 plus PB sine omega t minus kx1 plus delta phi. So this net pressure variation will then become some net amplitude, let's say P naught into sine plus some net phase constant, let's say epsilon, where once again, to understand this resultant pressure amplitude, we just need to develop the phasor diagram. So if this is the pressure amplitude due to the first source, and this is the pressure amplitude due to the second source, and this is the phase difference delta phi, then the net pressure amplitude or the resultant pressure amplitude it becomes this over here. This is the net amplitude. So that net amplitude is given by this familiar formula. So as I said, nothing new over here. It's just a repeat of that same analysis. And you will see this kind of repeat of analysis happening in one more chapter, wave optics, when we come to that later. And there'll be definitely a few questions from this entire section of interference of waves of all the three types, transverse waves interfering or sound waves interfering, or light interference of light experiments and questions based on that. So this is something both important, but at the same time scoring at the JEE mains as well as advanced level. It's somewhat like you can say heat and thermodynamics, more scoring than mechanics or even electromagnetism for that matter. Less likely that you will make mistakes if you've done enough practice. Okay, now what happens is, because there is no foundation that the waves are traveling along a string or something over here. They can be waves coming from any direction, coming from two separate sources. So the type of questions you can get related to interference, the numerical questions can be a little bit more interesting. Okay, so let's look at some examples. So now, for example, we can have a question like this, where you have a situation like this, that this is the position of a detector, and the detector can move along this line. Now, also with respect to the detector, there are 2 point sources which are located here and here. So detector is starting from this position. Actually, one thing before we start with a question like this, just additionally one more point we'll discuss about, which is also something that actually, the condition for constructive and destructive interference. So we'll just discuss about that and come back to this question. So here you can see that for delta phi being an even multiple of pi, where n is integers, it's cos delta phi becomes +1. So the net amplitude becomes the sum of the individual amplitudes. So net amplitude is equal to sum of individual amplitudes. And this situation is called constructive interference. Now, because in sound, what happens is, this thing is also very important, intensity. So we'll also express what happens in terms of intensity. So what happens is, in terms of intensities, if IA is the intensity of sound from source S1 in the above diagram, so IA is proportional to PA square. So IB is the intensity of sound from S2, and likewise IB is proportional to this one's pressure amplitude square. So now what happens is that the net intensity that I net becomes proportional to P naught square, where P naught is the net amplitude. So we can see that this formula also tells us that this is the resultant intensity in general. Actually, we should write over here the phase difference is delta phi, because we've used that notation. That is there. And the case of constructive interference, so we'll come back to this. we should use the notation where this is P naught. Because we've written P naught as the net intensity, net amplitude. So net amplitude equal to the difference of individual amplitudes. So this is the condition for destructive interference. So this is constructive and this is destructive interference. So now this is the general formula. So we can see from this that the maximum possible intensity we can get will become I1 plus I2 plus 2 times square root I1 I2. This is the case for constructive interference. And the minimum intensity we can get from the interference is when destructive interference happens. So that will become this. So this is destructive interference. Okay. So incidentally, this can also be written as square root of I1 plus square root of I2 whole square. And this can also be written as square root of I1 minus square root of I2 whole square. This is just another way of expressing the maximum and minimum possible intensity. And in general, for any value of delta phi, the intensity becomes like this. So just make a note of this, people. Okay, so we can write the above net pressure amplitude formula also in terms of net intensity formula, and then further look at the two special cases of constructive and destructive interference in this sense. Okay, let's come to our particular question now. So in this question now, what is happening is that S1 and S2 are 2-point sources such that it is given that the distance OS1 is equal to OS2 is equal to 2 meters, and a detector, so S1 and S2 are 2 fixed sound sources of equal frequency F and synchronized. That means in phase. Now detector D starts from a point shown such that S1D is equal to S2D, and OD, that distance, is equal to 3 meters. Now D moves along the line shown. So given that speed of sound is 300 meters per second. Actually, in normal atmospheric conditions under standard temperature, it is more like about 342 meters per second. But in this question, let's assume that the temperature of air is lesser, or for some reason the density is more, or something like that. So the speed of sound is 300 meters per second, and the common frequency of the two sources is equal to just tell you, 75 hertz. Yeah, but typically, Jagannath, in this type of question, they'll definitely mention the speed of sound. So frequency of the two sources is 75 hertz. Okay. So now, first of all, if this point is P, the point which is perpendicularly opposite S2. Okay. So what we have to do here is find the phase difference of sound from S1 and S2 initially at the detector's position. Then once again, the phase difference of sound from S1 and S2 as D reaches the point P. And finally, as D moves to a large distance, X is very much larger than the distance of S1, S2. So as it moves through a large distance from its initial position, find the number of positions at which experiences constructive and destructive interference. Okay, so this is a very typical type of question at JEE level involving interference of sound waves. Yes, S1 and S2 are two stationary fixed sources of sound. What of equal frequency, which is also given to you later, 75 hertz. Speed of sound is given to you. And then all this geometrical stuff is given that. And most importantly, what is given to you that the two sources are synchronized, they are in phase. Okay, people. So let's understand the fundamentals of this question first. So first of all, we are using this information given that the frequency of each source is 75 hertz and the wave speed is 300 meters per second. So the wavelength becomes how much? It becomes 4 meters. So lambda is equal to 4 meters. Now you see the first part of the question, when the detector is at the position which is sort of the midpoint of, opposite to the midpoint of these two. So at that point of time, the detector is equidistant from them. No? So the path difference is 0 at this point of time. When the detector is here, this distance x1 and x2, so path difference is 0 and there is no initial phase difference. So that means waves from the source S1 and S2 are in phase because the sources themselves are in phase and the waves are traveling same distance. T1 will be some amplitude sine omega t minus kx. T2 will be some amplitude to sine omega t minus k into same x. Okay, so that's the first part. But second part is where the geometrical calculation things start to begin. So now our source has reached, rather our detector has reached this position here, opposite to S2. So this is where your calculations will begin. What was given to us is that this distance was given to us as 3 meters. And this distance is equal to this distance, which is 2 meters. So now the wave that is reaching from here, from this source, is traveling a distance, let's say x1, and the wave that is reaching from this source is traveling a distance x2. So you can see that at this position P, there is some phase difference. Okay. You can see that x1 is 5 meters, x2 is 3 meters. So there is a path difference of 2 meters. So correspondingly, there's a phase difference. So that is where the calculation of lambda that we have done above becomes the most important thing.
Sir,
Yes.
why are we assuming that there is no Q naught phase differences like K del X plus Q naught? No? So how are we assuming that Q naught?
Because the question told us that the two sources are in sync.
In phase.
Okay, this part, this was an important information that the two sources are synchronized or in sync or in phase. Okay.
Okay.
Without that information, we could not have said that. So it's part of the question in this case. Okay, so anybody calculated the phase difference now from this? You got this? So you can see the phase difference at that point is becoming pi, right? So delta phi is becoming pi. So there is destructive interference happening. Okay. So you see that what is happening, that at now, once we understand this, we can also see one thing, that as your detector is moving further and further down this axis. Okay. So let's say this was his original position. Now I'll take this position as x equal to 0, suppose. Okay. And he is moving along this direction. Okay. So at x equal to 0, the phase difference was 0 because the path difference was 0. So here the path difference delta x was 0, so the phase difference was 0. Then by the time we came to this position here, this point P, our x would have been equal to 2 meters, right? Because this distance is 2 meters. Our path difference was becoming how much over here? That was also becoming 2 meters. And our phase difference was becoming pi. Now you will understand one thing, that as we go further and further down this, the path difference keeps increasing. When we go to a general point like this, the larger the value of x, the more the value of path difference. So you can see now here, this delta x is going to be greater than 2 meters. So larger the value of delta x, of x, okay, the greater is the path difference. So like that, now if we imagine that we've gone to a point which is very, very far away, some point like this, where over here x is very large compared to that distance s1, s2. So at this point, what will happen? My path difference will almost tend to become equal to s1, s2, because these two lines will almost become parallel to the x-axis. So the path difference will almost become equal to 4 meters. So here the phase difference will almost become how much? It will become 2 pi, because my lambda was the same. Because lambda was equal to 4 meters. So you can see, so as the detector moves from x equal to 0, okay, towards x tending to infinity, we can say. Okay. The path difference goes from delta phi equal to 0 to delta phi tending to become, sorry, this is a phase difference, tending to become 2 pi. Or you can say path difference which is 2 lambda. So which is lambda. So what is happening in this kind of a situation is that, therefore, only one position of constructive interference at x equal to 0 and one position of destructive interference is experienced. And eventually, as x tends to infinity, delta phi tends to become 2 pi. But this is not really experienced because at such a large distance, the sound intensity will be too low. So the sound intensity from the sources S1 and S2 would have become too low. So you don't really experience any constructive interference. Okay? You don't experience any sound at all, let alone any effect of interference. So the distances are just adjusted in this particular situation in such a way according to the wavelength of the sound, or the relationship between frequency and wave speed, that it so happens that only one position of constructive interference and one position of destructive interference is experienced. Or let's say the detector was going from minus infinity to plus infinity. Then on either side of the origin at a distance of 2 meters, you would experience two destructive interferences. And exactly at the origin, you would experience one constructive interference. Everywhere else, you would experience interference which is neither constructive nor destructive, because the phase difference would be such that your cos phi is neither +1 nor -1. There's something in between. Okay, people, so hope this concept is clear to all of you.
Yes, sir.
Now, another very common type of question like this now, of the same type of concept, is that instead of the detector going along a straight line like that, the detector is moving along a circular path. Okay. Let's say the detector is moving along a circular path like this. Okay. And with respect to the circle, or you can say with respect to the center of the circle, at two symmetrical positions, we place two sources. Okay. So S1 and S2 are symmetrical with respect to, so S1 and S2 produce sound of same frequency f and wavelength lambda. Okay. So if OS1 is equal to OS2 equal to 3 lambda, okay, then as the detector completes one cycle, okay, of a circular path, one cycle, not one cycle. Okay. So one cycle of the circular path, you have to find out how many positions he will experience constructive and how many positions destructive. Okay. Now notice in this question, it is not given to us that the two sources are in phase. Okay. And I'm just giving you a hint that that will not affect the answer. Okay. That how many positions you will have constructive interference versus how many positions you will have destructive interference, that will not be affected by whether or not the sources are in phase. Exactly where the constructive interferences and where the destructive interferences, the actual locations, that will be affected by the phase difference, if any, between S1 and S2. But the number of positions where phase difference, I mean, where constructive or destructive interference is happening, that will not be affected by whether or not the sources are having any phase difference. Okay. So try to focus on what I've just told you and try to understand why that is the case, and also calculate. Okay. So if you just understand that it's not going to be affected, you can always solve the question assuming that S1 and S2 are in phase. So if you assume S1 and S2 are in phase, as the detector is moving on that circle, you can see at which position the path difference is maximum and at which position the path difference is minimum. And from that, you can understand what is the range of path difference. It's going from a maximum to a minimum. So in that range, you can again see how many times you will get constructive interference and how many times you will get destructive interference. So I'll explain this in a minute. Just try to attempt this yourself. Yes, very good, Divan. So what we'll see is like if we take a general sort of position like this, where we take this angle as theta. So you can see that there's a path difference between these. So if this is x1 and this is x2, you can see that at theta equal to 0, the path difference x1 minus x2 has a magnitude of 3 lambda. So the phase difference 2 pi by lambda delta x. So assuming sources are in phase, S1 and S2 are in phase. So the inherent phase difference between them is 0. Okay, so then that is equal to how much now? 6 pi. Okay. And theta equal to pi by 2. So let's say I'm calling this position A, this position B. Our x1 minus x2 becomes 0. So our phase difference becomes 0 at B. So what is happening as you go from A to B, your phase difference is going from 6 pi to 5 pi to 4 pi to 3 pi, 2 pi to pi to 0. So this is constructive interference. This is destructive interference. This is constructive. This is destructive. This is constructive. This is destructive. This constructive. So there is constructive interference here. There is constructive interference here. Okay, but in between, there is destructive interference somewhere. Then again constructive interference somewhere. Then again destructive interference. So the phase difference is going from 6 pi to 5 pi to 4 pi to 3 pi to 2 pi somewhere to pi somewhere. Okay. So again on this side also it will be the same. So you can see that there are so in all there are 12 positions of constructive and 12 positions of destructive interference. In one cycle. Theta is the angular position of any point. Na? Theta is just this angular position. So theta equal to 0 corresponds to this point A, where the path difference is maximum. Okay. And theta equal to pi by 2 corresponds to the point B, where the path difference is minimum. So every time you go from this kind of position, so even in the second quadrant, as you go from pi by 2 to pi, now your path difference is increasing from 0 to 3 lambda, like that. So now the thing is, suppose S1 and S2 had some initial phase difference, then A would not be a point where the phase difference would be 6 pi. It would be 6 pi plus phi naught or 6 pi minus phi naught. But the point is, as you're going along the circle, again, your phase difference is going to have that same range. The maximum value is 6 pi and the minimum value is going to be 0. So this is going to repeat 12 times, where they are having even multiple or odd multiple of pi, including 0. So these are typical type of questions involving interference of sound waves. Okay. So you can start doing questions from H.C. Verma, interference of sound waves. Next time we will discuss the other two types of superposition of sound waves, that is standing waves and also beats. And with that, then we'll have just one additional effect left, which is called Doppler's effect in sound, and we'll complete sound with that. So that's it for today's session, people. Wish you all the best. Have a nice day.
Thank you.
Thank you, sir. Thank you, sir.
Thank you, sir. Bye.
Thank you, sir. Bye.
Okay, Shikhar. So I'm explaining the whole thing again. See what is happening. The 2 points S1 and S2, they are lying on this horizontal axis. No? So when you are at the point A, you can see the path difference, that is from S1 to that point and S2 to that point. The difference of those two lengths is maximum, no? And that is equal to 3 lambda. Okay, actually, what we have taken here is that this is lambda by 2. Okay. So that is why that distance is equal to S1, S2, which is 3 lambda. So the phase difference is maximum 6 pi. Now, as you move from A towards the point B, you will see the difference between X1 minus X2 starts reducing and it becomes 0 as you reach the point B. So every time you're going from a horizontal diameter point like A to a vertical diameter point like B, your path difference is decreasing from 3 lambda to 0. Then as you're going from B to the horizontal diameter on that side, again your path difference will start reducing, will start increasing from 0 to 3 pi. So similarly, that same thing is happening to the constructive and destructive interference. As your path difference is changing from 6 pi to 0, 6 pi it is constructive. As it reaches 5 pi, it is destructive. Then again 4 pi it is constructive. And again 3 pi it is destructive. So as you go from 6 pi to 0, you can see that at four particular locations, you have constructive interference, and 3 particular locations you have destructive interference. So like that, now I've labeled for each quadrant what is happening. Okay. Okay, good. Yeah, so that's what I said. If the initial phase is not 0, then the location of these constructive and destructive interference points will be different, Jagannath. But the number of points will again be the same, because the range of the phase difference will again be between 0 and 6 pi. It's just that the phase difference will offset where the constructive interference positions is and where the destructive interference positions is.
Okay, so we're taking it as 0 only for easing the
To
calculations.
give you an example, okay. Now, so for example, if the phase difference is pi by 2, then you can see at the point A, the net phase difference would have become 6 pi plus pi by 2 or minus pi by 2. No, so accordingly, we'd have to adjust the position of the constructive and destructive interference. But the total number of constructive and destructive interferences would be the same.
Okay, so will we be doing any example where they are not in phase?
Yeah, we'll be doing that. Like we've taken examples in transverse waves also, no, where we give some time delay to one of the sources, like those kind of examples.
Okay, sir. Thank you. Sir, just a second. I had to write down something.
Yeah, you can finish.
No, it was above this.
Achha, the part above this.
Yes. Yeah, that's it. Sir, sir,